This lesson is entitled Limits when Given an Equation. Now, we've already explored, as you approach a point, choosing a number close to that point and putting it into the equation to find out approximately what the limit is, or see if there's a pattern such that we can forecast what the limit is going to be. We've also looked at graphing functions and finding the limits when given a graph. Now we want to find out what techniques we could use if we're simply given the equation straightforward. So here we start with example 1. Find the limit of the function 3x cubed plus 2x squared minus 5x plus 9 as x approaches 2. Well, first thing we're going to do is we're going to plug in. That is, we're going to evaluate this function when x is 2. So we have 3 times 2 cubed plus 2 times 2 squared minus 5 times 2 plus 19, and that is 31. And that is our answer. Now, you should always try as your first step, now this is very important, as your first attack on a problem when given an equation, see if you can plug in and if you get an answer. Now, of course, you can double check yourself by simply taking a number close to 2, such as 2.1 or 2.01, and evaluate the function for that and see if your answer 31 looks like it's reasonable. Or you could actually put 3x squared plus 3x cubed plus 2x squared minus 5x plus 9 into your calculator and graph it and see from that if it looks like the limit is 31. I don't advise either of those two procedures other than to, if you're not sure of your answer, to double check it. But now the question always comes up at this point, could we just graph it and avoid doing any of this work on finding the limits when given an equation? Or could we just choose a number close to the value it's approaching and plug that in and see? And the answer is no. That may be used as a check. But the directions when you have problems such as this, when you're given an equation, is going to read as follows. Find the limit of the following equations, show the algebra that you use, and that's the catch. In other words, if you just try to sidetrack or sidestep the directions to get the answer only, you'll get no credit. Simply plugging in or looking at the graph is simply offered as a way to check your work. So let's go to the next slide. Here we have example 2. This time we want to find the limit of 3x squared minus 7x plus 2 over x minus 2 as x approaches 2, and we'll first try plugging in. And when we do, we get 0 over 0. Now, what that tells me is that I cannot plug in. But now pay attention here. This is valuable information. Usually, if you get 0 over 0, that means that it has a limit and there's some way to do it. You've just got to figure out what that is. That's valuable information, people. So what we're going to do here is we're going to factor the numerator, which is 3x squared minus 7x plus 2 factors as 3x minus 1 times x minus 2 over x minus 2. Now, I smile when I see that factorization. Why? Because, look, here's the problem. The problem is this denominator, which is 0. The problem is not the numerator. A numerator of 0 is okay. 0 over 10 is 0. It's when you have 0 in the denominator that's a problem. So if this is going to work, we've got to get rid of this x minus 2 denominator. Now, this gives me hope when I see this x minus 2 in the numerator and the denominator. Now, I still cannot plug in at this point. However, remember, and this is most important, remember the difference we said at the very beginning between algebra and calculus as far as limits go, or a function goes. In algebra, we are interested in what happens at the point. In calculus, we're interested in what happens close to the point. So we're interested in what happens close to 2. Well, as long as you don't put in 2, then you can cancel these two values, okay? Now let's put a number close to, well, there's no reason we can't, if we cancel these out, there's no reason we can't put in 2 itself. And when we do, we get 3 times 2 is 6 minus 1 is 5. And that's the limit. Now, you can check yourself out on your own to see if you're right. But remember, if it says do it by algebra, we will not accept the answer. We must see, in this case, this factorization. By the way, we'll emphasize this over and over and over again. You do not drop the LIM in a limit problem until you get to the step where you plug in. Keep that in mind. That's important. A lot of students fail to notice that, and it's bad mathematical grammar to do that. Okay. Bad mathematical grammar, okay, to do that. And you understand what I mean by grammar. It's just like you may in a sentence say something, people understand what you're saying, but it's grammatically incorrect. Let's go to the next problem. Example 3. First step is always plug in, and when you do, you're going to get in the numerator square root of 5 minus, you'll get square root of 25, which is 5 minus 5 is 0, and of course the denominator is 0. So we cannot just plug in. However, remember people, 0 over 0 tells me there's probably something I can do. And what I'm going to do is something that you learned in algebra, and that is, we're going to multiply the numerator and denominator by what's known as the conjugate of the numerator. Now, the conjugate of the square root of x minus 5 is the square root of x plus 5. The conjugate of a minus b is a plus b, or the conjugate of a plus b is a minus b. Now, the reason we're going to do this is because when you multiply conjugates, as you see here, you get no middle term. When you multiply conjugates, when you multiply a minus b times a plus b, you get a squared minus b squared, no middle term. So we're going to multiply the numerator by the conjugate, but we can't just do that. We've got to do it to the denominator as well. So we're going to multiply the numerator denominator by the conjugate of the numerator. And when we do, this is going to be the square root of x squared, which is x, minus 5 squared, which is 25, over x minus 25 times the square root of x plus 25. Now notice, I've got, I can smile, look at this, x minus 25, x minus 25. It makes me believe I'm onto something. Now, remember, I can't put in 25 here, but I'm not using 25, I'm using a number close to 25, so I can cancel these, and now I get 1 over the square root of, let's go ahead and put the 25 in, so that'll be square root of 25 is 5 plus 5 is 10, and there's my answer. Now, one thing I want to say before I leave this problem, notice, I start at the problem, LIM, LIM, LIM. Then I drop the LIM. Why do I drop the LIM? Because the difference between this step and this step is I have put in the 25. I've plugged in. You cannot drop the LIM until you get to the step where you substitute in the point you're approaching. make sure you understand that. Look at this on every one of the problems we're working here and see if we're not faithful to that. Of course, you could check it by taking a number close to 25, like 25.01, plug it into your calculator and see if you indeed get very close to 1/10. However, that's simply to check. It's not acceptable work. Now, before we leave this problem, I want to make one other observation. There is another way of looking at this problem, and that is look at this denominator as x minus 25 and treat that as the difference of two perfect squares. You say, what do you mean? Well, x minus 25 is the square root of x minus 5 times the square root of x plus 5. You see that? If you multiply the square root of x minus 5 times the square root of x plus 5, you get square root of x squared, which is x, and 5 squared, which is 25. Okay. Basically, it works because you're writing this as the square root of x squared minus the square root of 5 squared. Now, you can do that. I've watched students do this, and it's acceptable. Here's the problem. We need this technique of conjugates a little later in the course, and we're going to have to eventually use it. I suggest you use the given approach above, multiplying by conjugates. That'll work in any class. But I suppose most teachers would accept an argument for what you've done here, but you've got to be able to explain that. Okay, are we all right? Let's go to example 4. Now, this one's a little different. You notice when we work problems, each problem shows something different. We've said this from the beginning in this course. This is a problem. This problem is harder. What makes it harder? Well, the fact it's harder is that we've got x cubed minus 27 over x minus 3. And when you put in 3, of course, you get 3 cubed, which is 27 over 27, which is 0, over 3 minus 3, which is 0. So we get 0 over 0. So that tells me there must be something I can do here. Well, what I'm going to do is, and you may or may not have had this in your algebra courses, second-year algebra courses, pre-calculus courses, but it's factoring the difference of two perfect cubes. And we would like for you maybe to know this. When you factor the difference of two perfect cubes, you get a minus b times a squared plus ab plus b squared. Now, let me show you what's happening here. Take the cube root of a cubed. What's the cube root of a cubed? A. What's the cube root of b cubed? B. Put this sign between it. Then square this term. Multiply the two together and give it the opposite sign. So it's a times b, and this is minus, so make it plus, and then square the last term. You know, you cannot factor the sum of two perfect squares, but we can also factor the sum of two perfect cubes. That goes like this. Take the cube root of the first term, that's a. Take the cube root of the second term, that's b. Put the opposite of this symbol between them. So this is plus. So we're going to, put this symbol between them. I'm messing you up here. Take the cube root of this, which is a. Cube root of this is b. Put the symbol between it. Then square this term, a squared. Multiply the two together and put the opposite sign, which is minus ab plus b squared. You're not going to use this often, but we're going to use this as our technique of doing this problem. The thing of it is, you can always do the difference of two terms that raised to a power if it's an odd power. In other words, we could do, say, say x to the fifth minus 32, because it would be 32 is 2 to the fifth power, but we're not going down that road. So don't get too worked up over this problem. We just want to show you, before we leave this factoring, that all kinds of factoring are in possibly in your arsenal. So we're going to Cube root of this, which is x, cube root of this is 3. Put this sign between them. And then we're going to square this term, x squared, multiply the two together, 3x, and give the opposite sign as plus 3x and square the last term. Now, I feel good about this. Why? Because look, x minus 3, x minus 3. Now, remember, we don't get to 3, so we can cancel here. These go away, and now we simply put in 3, and we get 27 for our answer. It's example 4. Now let's consider example 5. Let's plug in. First thing you should do is plug in. When I do, I get 14 over 0. Now, when you get an answer, when you plug in, that's the limit. If you get 0 over 0, that means that you can't plug in, but you should be able to find a limit by some method of mathematics, precisely like conjugates, factoring, or what have you. This tells me that there is no limit. There's nothing I can do. Nothing I can do. Okay? In other words, I'm going to quit. So actually, when you get an answer of a number, that's something to smile about. That's the answer. When you get an answer of some number over some number other than 0 over 0, that's something to smile about. It tells you, in other words, you can quit in both cases. You don't have to do anything. It's only when you get 0 over 0 do you have your work cut out for you. Now let's look at example 6. This is what we call a piecewise function. It's broken up into 2 parts. This function is equal to x squared plus 1 when you put in numbers smaller than or equal to 2. This function is equal to x plus 3 when you put in numbers larger than 2. And we want to find the limit when you take when it approaches 2. So this time we got to do something a little different. We can't just plug in. We can put in 2. When we put in 2, we're going to get, in this case, 5. But this is not going to show because that is the limit. Because if we looked at it graphically, you might see this. And if example 6 doesn't verify for you, the next example will. But so let's look. What we want to do is we've got to check this out by taking a number to the left of 2. Now, to the left of 2 means smaller than 2, which means you put in to this function right here. And when we do put a number smaller than 2 in, you're going to get 5 for your answer. When you put a number bigger than 2 in, there's a number to the right of 2, which we have here, you're going to get 2 plus, you're going to also get 5. Now, since you get the same answer to the left as you do from the right, remember, that's the limit. We said this earlier. The limit, if the limit is the same from both the left and right, that's the limit. If it's not, then it has no limit. Okay? This is called a piecewise function. The reason it's called a piecewise function is because it's divided up into 2 pieces. It's on this graph, which happens to be a parabola for numbers less than or equal to 2, and it's on this graph, which happens to be a straight line for numbers greater than 2. But be that as it may, it does have a limit. Let's go to the next problem. Example 7 is another piecewise function. Now this says that this function is equal to x squared plus 2, which is a parabola for numbers less than or equal to 4, and is equal to 4x plus 3, which is a linear straight line function for values greater than 4, which the limit as x approaches 4. Well, we're going to take a number, with this time we'll take a number to the right of 4. To the right of 4 means I'm going to use this function. Right of 4 means bigger than 4, right? So this says for bigger than 4, use this function. And when I do, I get 4 times 4, 16 plus 3 is 19. Now, for numbers less than 4, I'm going to use this function. And when I put into this, I get 4 squared, which is 16 plus 18. They're not the same, so the limit does not exist. Let's look at example 8, another piecewise function. This says the function is equal to 5x plus b. B is some number. What number? I don't know. For numbers smaller than or equal to 2. It's equal to x plus 7 for numbers bigger than 2. And here's what the question is. For what value of b does the limit as f of x approach to exist? So remember, they've got to be same on both sides. So number to the left of 2, smaller than 2, means we use this function. And when we put in 2 into this function, we'll go get 10 plus b. For numbers to the right of 2, we're going to use the x plus 7 function, greater than 2. And that's going to give us 2 plus 7 is 9. These have got to be equal if the limit exists. So set them equal to each other. In other words, 10 plus b equals 9, so b is -1. Now, we could continue to do problems over and over, more and more problems, but we choose not to. We've shown you the basics of what you've got to be able to handle. You've got to plug in. You've got to be able to do factoring. You've got to be able to multiply by conjugates. You've got to be able to handle, realize that if you end up with 0 over 0, it pretty much has a limit. If it ends up with some number other than 0 over 0, then you can quit. The limit doesn't exist. And then we've looked at piecewise functions. Let's wrap this topic up by talking about some things that might be helpful for you to know. If you take the limit of a constant, it's the constant. Take, for example, the limit of 5, the function 5, y equals 5, as x approaches 2. Well, that's pretty much, 5 is really 0x plus 5. And so if you put in that, any number for 2, you're still going to end up with 5. In other words, the limit of a constant is always 5. And a constant, in this case, x is a variable, so anything, doesn't have to be a number. If I told you the limit of y as x approaches a is, what is it? Or m as x approaches a, it's m. I mean, you know, this tells you what the variable is. This doesn't have an x in it, so it serves as a constant, or is a constant, and so know that fact. Don't belabor it. Just, it's acceptable just to give the answer. The limit of the sum of two functions is the sum of the limits. In other words, if you have the limit of something and another function over here, you can take the limit of the first function, limit of the second function, and you may add those two answers together. If you have a number in front of a function, say if you have 5 times, say, x cubed, as x approaches 2, you can find the limit of x cubed and multiply your answer by 5. So the limit of a number times a function is the number times the limit of the function. If the limit of the product of two functions is the product of their limits. Get that? The limit of a product is a product of the limits. And the limit of a quotient is a quotient of the limits. Always we have to make the disclaimer in this case, provided the denominator is not 0. And if you, this one's really helpful here in number 6, we see here, the limit of something to a power, find the limit and then raise the answer to this power. For example, if I had 2x plus 3 to the 10th power, I certainly don't want to have to multiply out or expand the 2x plus 3 to the 10th power out and then take the limit. I would take the limit and then raise that answer to the 10th power. And it would be much easier. Last thing we're going to say. when you have a limit problem that involves an equation and it says to do it by alpha, step one, always plug in. Step two, try factoring. Step three, try multiplying by conjugates. Be willing to accept the fact that sometimes the limit does not exist. And I want to reiterate, never drop the LIM until you get to that step where you plug in. And notice we've done that all the way through in this particular lesson. So that concludes this lesson.